Okay. Now in the previous sessions, we just finished the time domain analysis of the first order and second order system, which include the transient and steady state. That is the complete time domain analysis, okay, of a first order, second order, and we solve the problems also, okay. Now, I just ask one question first, you just try to answer for that. Now, this is an open loop transfer function. This G of S is an open loop transfer function. Now what he is asking is, he is asking to find the stability of the closed loop control system. Now this is the open loop control system transfer function, and one open loop pole is available at origin. This is the open loop pole is available at origin, and the open loop control system is marginally stable, but some of the students are saying the answer is directly marginally stable. What he is asking? He is asking to find the stability of closed loop control system. Now for stability of closed loop control system, now first you should find the characteristic equation. What is the characteristic equation? 1 plus G of S equal to 0. Therefore 1 plus, what is the forward path gain? The forward path gain G of S is 1 by S is equal to 0. Therefore S plus 1 equal to 0. Therefore S equal to minus 1 is the closed loop pole. Therefore now the closed loop pole is minus 1. Now when the closed loop pole is at minus 1, now this is the closed loop pole such that the closed loop control system is stable. This is a very easy question, am I not? Now he is giving an open loop control system and he is asking the stability of the closed loop control system, which is very simple, you can easily find. Open loop control system is marginally stable. Open loop control system is marginally stable, whereas its corresponding closed loop control system is stable, am I right or not? So now the question is, whatever maybe he is giving, you want to find the stability of the closed loop control system, you can easily find, okay. Now similarly, then I ask the second question. Before that, you first do this one, okay, you just take this one. Now in the same manner, I ask one more question. Find the stability of the closed loop control system. Now this is the open loop control system transfer function. Now the question is, what is the stability of the closed loop control system? Find the stability of the closed loop control system. Now this is the characteristic equation. Now you first find the characteristic equation. The characteristic equation is the closed loop control system poles are available. So this is the characteristic equation, S power 7, 8 into S power 6 plus 10 into S power 5 plus 2 into S power 4 plus 12 into S cube plus 3S square plus 5S plus 100 equal to 0. This is the characteristic equation. The highest power in the characteristic equation, which we called as order. Therefore, this is the 7th order. Okay, this is the order 7. Order 7. Then you use your calculator or you find the roots, whatever you want, you do it, and tell me the 7 roots. And what are the 7 poles? Where are the 7 poles? And if you know the 7 poles, then only you decided the closed loop control system stability or not. Now previously you can easily say the answer, but now this question, now you are struggling. Am I not? You are not in a position to find the 7 closed loop poles, and you are not in a position to identify the 7 closed loop poles. Where it is? Now where is on S-plane? I don't know. So you cannot say the closed loop control system stability. That is the problem in this question, but in the previous question this kind of problem is not facing. Am I not? Why? Because the previous question is just only for first order, second order. Now but this is of order 7. which means that when order is increases, it is very difficult to do the analysis of the closed loop control system, because it is very difficult to find the closed loop poles, and it is very difficult to find the stability of the closed loop control system. Understand or not? So, but now whatever previous sessions which we are finished is maximum second order we are doing. Am I not? That's why we are not facing any problem. Even the second order you can easily find the roots. Okay. But third order, fourth order, fifth order, sixth order, seventh order, like that, when order is increases, now we are unable to do the analysis of the closed loop control system. At least the stability of the closed loop control system is a problem for us, because to choose that system, now at least one parameter I want to know it. What about the stability? Is the system is a stable system? Then I want to be considered. So what is the technique we have to be used here? So I am not able to solve this question. Therefore, we required some help to solve this particular issue. Now that help is already given by two scientists, which is called as Routh and Hurwitz. This is Routh and Hurwitz. They are implementing one method to find the stability of the higher order systems. Now that is called as Routh Hurwitz stability criteria, or simply called as RH criteria. RH criteria or Routh Hurwitz stability criteria. Now this Routh Hurwitz stability criteria, now these two scientists will give one method to solve the stability of the closed loop control system if order is more. Okay. So what is the method which is given by Routh and Hurwitz? Will follow that method, and if you understand that method, and it is very easy to solve the problem of higher orders, even 7 or 6 or 8, 9, 10, whatever it may be. Okay. So that is the reason why now we are taking a help of the Routh Hurwitz stability criteria. Now our next topic is Routh Hurwitz stability criteria. Okay. Now our next topic is Routh Hurwitz stability criteria. Okay. Now, sir, then how to solve this question? First you see the Routh Hurwitz stability criteria. Then after that we can come back to this particular problem, or any problem you can easily solve. Now I will give a few important points on this Routh Hurwitz stability criteria. What this Routh Hurwitz stability criteria will provide, will give us. Okay, we'll discuss one by one, point by point. Now this RH criteria is used to find the stability of the closed loop control system. Now this is used to find stability of closed loop control system. Right? Yes, we have the closed loop control system only when order is increases because of the feedback. Now when open loop no feedback, closed loop feedback, location is changing, as order increases it is difficult. Okay. Now what is the features of RH criteria? And another feature of RH criteria is Routh Hurwitz stability criteria is used to find the stability of the closed loop control system, and RH criteria is used to find right hand sided poles, left hand sided poles, imaginary axis poles. How many poles are on the right hand sided? How many poles are on the left hand sided? How many poles are on the imaginary axis? Now the RH criteria is to find the number of poles is on the right hand side, left hand side, on imaginary axis. Sir, then if you know how many poles on the right hand side, if you have a confidence of that this many number of poles is on right hand side, and answer is very simple. Now one pole is on the right hand side, system is unstable. So this RH criteria is used to find the number of poles on the right hand side or left hand side or imaginary axis. That is another feature of the RH criteria. And another feature of the RH criteria is the RH criteria is used to find the range of K values, for stable, unstable, marginally stable. What is the system gain? For what range of K it should be stable, for what range of K it should be unstable, for what range of K it should be marginally stable. Like that, the RH criteria is used to find the system gain K ranges. And not only that, the RH criteria is used to find K margin and frequency of oscillations. What is marginal value of K and what is the frequency of oscillations if system is marginally stable. If the system is marginally stable, what is K margin? What is the frequency of oscillations? Now, what is the range of values of K such that system is marginally stable? What is the frequency of oscillation? And RH criteria is used to find the another topic, which is relative stability. The RH criteria is used to find the relative stability of the system. What is relative stability also we'll see. Okay. Now the RH criteria is used to find the relative stability. Whatever you want to do it, now you have to obtain all these particular features. Now with the help of Routh Hurwitz stability criteria, we have a characteristic equation. We have a characteristic equation. Then only we can have all these particular analysis. We have a characteristic equation, then you can able to solve, you can able to get all these particular features. Okay. Now this is the RH criteria performance and significance role of the closed loop control system. It is used to find the stability of the closed loop control system, and number of right hand sided, number of left hand sided poles is identified, and range of K and frequency and K margin, a relative stability concept. And to do all these things, we must and should require a characteristic equation. Now first we will see the RH criteria technique method, now a general method, and after that we will implement that method for all the problems. Okay, first you take this. So don't worry, we will check one by one the feature. Now after finishing of RH criteria, you have all these particular things. So whatever you want to do it in the RH criteria, now we must and should require a characteristic equation. Okay. Now this is the characteristic equation. Now this is the characteristic equation, which is 1 plus g of s h of s equal to 0, a naught s power n, a1 s power n minus 1, a2 s power n minus 2, plus and so on, plus a n minus 1 into s plus a n is equal to 0. This is the characteristic equation. Now the highest power in the characteristic equation is n, therefore this is the nth order system. Therefore I am giving the solution for nth order. Then once if you understand the solution for nth order, we can easily solve the any order characteristic equation. Is it right or not? Yes, we can easily solve any order characteristic equation if you know the procedure for nth order. Okay. Now the students, you just try to understand. Now this is s power n. The highest power in the characteristic equation is s power n. Okay. The highest power in the characteristic equation is s power n. Now see this s power n. First of all, it is an even power and odd power. Okay, so that you have to identify. Now let us assume this n is an even. Okay, I am assuming this even or odd, not a problem. Now this n is even. If the highest power is an even power, write all the even powers in that particular row. Let us assume, for example, the highest power is an odd power, write all the odd powers in that particular row. Okay, so I am assuming this n is an even power, write all the even power coefficients, a0, next even power is a2, next even power is a4, next even power is a6, like that. Okay, next, like that you can write. Next, what is the next highest power? This is even power. Definitely the next highest power is s power n minus 1. If this is n even, this should be odd. Write all the odd power quotients, a1, a3, a5, a7, like this. Okay, for better understanding, I will take one small example, okay, such that you can easily understand. Now this is the characteristic equation, s cube plus 8s square plus 4s plus 2 is equal to 0. This is the characteristic equation of order 3. What I am saying, what is the procedure? First, highest power s cube. Now the highest power here, it is an odd power. Write all the odd power quotient. S power 3 quotient is 1. Next odd power is s power 1. S power 1 quotient is 4. That's it. Next, what is the next highest power? The next highest power is s square, is an even power. Even power quotient is 8. This constant is also treated as even power, or s power 0 quotient is also treated as even power. So constant or s power 0 quotient is 2. 0. Okay, understand or not? Constant or s power 0 quotient is also treated as even power. Like that, you have to identify the first two rows. Okay, first two rows. Now the students, one point I am saying, if you write the first two rows of any characteristic equation, all the coefficients in the characteristic equation must be presented in that particular table. 1 is present, 8 is present, 4 is present, 2 is present. In the first two rows, all the coefficients of the characteristic equations are presented in the first two rows. The coefficient of all the characteristic equation, all the coefficients should be accommodated in the first two rows. Okay, so once the first two rows are filled, with the coefficients in the characteristic equation, from the third row onwards we need to find the coefficients. Okay, from the third row, fourth row, fifth row up to last row, we want to find the quotient. First two rows, the quotients are given in the characteristic equation, and the third row we have to find. So for finding the quotients in the third row, then there is a unique procedure for that. Now this is s power n minus 2 is the third row. So use this notation. And one more thing, if you want to find the quotients of any particular row, the top of the row which is above to that particular row is the responsible row for getting the quotients. Okay, let us assume, for example, in the third row you want to find the quotients. Second row is the responsible row, and in second row first element is the starting for doing the calculations. Okay, again I am repeating. Fifth row you want to find the quotients. Fourth row is the responsible row, and a fourth row first element is the reference element. Clear? So now I want to find the quotients in the third row. Second row is the reference row, and first element is the reference element. And use this notation: one up arrow, one down arrow from here. Okay, from one up arrow, one down arrow. Tail, head, tail, head. Take tail and head product. If it is up arrow positive, down arrow negative. A1, A2 minus A0, A3 by, now the denominator is always the reference element. The reference element is A1. If you want to find the quotients in any particular row, then the top of the row is the reference, first element is the reference. If you want to find the quotients here, then this is the reference row, this is the reference element. just you should extended arrows to the next column. You just extended the arrows to the next column. So what is the style and head product? A1, A4 minus A0, A5 by A1. Now again, if you want to find the quotients here, every time third row quotients are finding from second row reference element is first element. Now from here again, extended the arrows to the next column. Extended the arrows to the next column. So A1, A6 minus A0, A7 by A1. Like that, you continue the quotients. Like that, you can continue. Like that, you can extended all the quotients. Okay, that's why I will take one example here. S power 1. So here it is. 8 into 4, 32 minus 1 into 2 by 8 into 4, 32 minus 2 by 8. Now this is 0, 0. Okay. Now 8 into 4, 32 minus 2, 32 minus 2, 30 by 8. Now next, S power 0. Now if you want to find the fourth row, third row is the reference row. So here, if you want to find the quotients here, now 8 into 4 minus 1 into 2 by 8. So how much here? This is 30 by 8. So now S power 0 row, S power 1 is the reference. This is the first element. Now let us assume this is some x. This is some x. Now x into 2, 2x minus 8 into 0, 2 into x, 2x minus 8 into 0, 0 by x. So 0, 0. So 2 cancel, sorry, x cancel. Therefore this is nothing but 2. Like that, you can find the quotient from the highest power to the least power. The least power is S power 0. Now here is also the same procedure now. S power n. Now next quotient is, next row is S power n minus 3. Find the quotients and so on. Like that, highest power to the least power S power 0. Now, sir, without calculating the rows coefficients, then how you can write the an is here? How you know this an is coming? And you also know that the last row is nothing but S power 0 row. The last row first element is a constant in the characteristic equation. Whatever may be the constant, that constant should be reproduced. That constant should be presented in the last row as a first element. Okay, you don't write directly. Okay, if you do this calculation and you can get the answer. So one significance is that last row first element is a constant. All your calculations are correct in between the tabular form. If the last row first element you should not get any constant, which means somewhere you do the mistake, so you go back and you rectify that. Okay, in that way also you can verify the quotients which is calculated by you is correct or not. Okay, if all are correct, the last row first element should be reproduced, should be repeated as a constant in the characteristic equation. Yes, this is a constant, therefore it is correct. Okay, this is called as Routh Hurwitz tabular form. Like this tabular form which consisting of a quotient is called as Routh Hurwitz tabular form. Now first you finish this Routh Hurwitz tabular form from the highest power to the least power and calculate all the coefficients, and any row coefficients you are calculated, and the top of the row is the reference row and the first element is the reference element. Use up arrow, down arrow symbol and extended that arrows to the next column. Once if you finish this, then the stability is decided by the first column. So see the first column coefficients, and there are 2 points you have to be identify that. Now first point, all the coefficients in the first column, should have same sign. Same sign means not positive. All are negative. All are negative means positive only. Okay. Now this is the first condition, and second condition, the first column coefficient should not be 0. All the first column quotient should have same sign, and all the first column quotient should not be 0. Okay. If these two conditions are satisfied, then in the RH tabular form, closed loop control system is 100% stable. Let us check this with the existing problem. See the first column. Positive, 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 positive. Condition 1 is true. Not equal to 0, not equal to 0, not equal to 0, not equal to 0. Now therefore, this problem is, whatever example we are taking, this is a stable system. Is it understand or not? This is a closed loop control system, 100% stable. Sir, how I can believe, sir? How I can know that that is correct or not? Order 3, now you use roots. You just try to find the roots of that particular order 3, and you said you find that roots. Definitely those 3 roots are lies on the left hand side. That's why system is stable. And tabular form is also saying that this is closed loop control system stable, and you can also find that the closed loop control system stable if you find the roots. Okay. Now this is the Routh Hurwitz stability criteria, now which is identified from the first column, because the first column quotients will use the roots which lies on the right hand side. Okay. Therefore all are same. Therefore all are stable. Stable means all are on the left hand side. If closed loop control system is stable, now all the closed loop poles lies on left hand side of S plane. When all the closed loop poles lies on left hand side of S plane, when the closed loop control system is stable. If the closed loop control system is stable, then this should be the thing which is existing. Okay. This is the procedure of any characteristic equation of any order. Okay. Note down this first. Okay. Now this is the 3 conditions which are valid if the closed loop control system is stable. No sir, condition 1 is failed. No sir, condition 2 is failed. Now in such situation also, what happen also we'll see. Now just take one small example such that we'll try to understand what happen if case 2 is failed. Okay. So with respect to these points, now this is the stable system. Okay. Now this example, whatever we consider, is a stable characteristic equation of order 3. Now let us take in Routh Hurwitz tabular form, the first column is like this. For the example, okay, this is for example. Like this, okay, for example, see here. If the first column is like this, example, this is for example, okay. I just take one example. Now what happened now in the first column? All the coefficient in the first column should have same sign, but this is positive, positive, but this is negative. Now sign is changes, am I not? Now the condition 1 is failed. What is the condition 1? If any sign changes, if any sign changes, if any sign changes in the first column, if any sign changes in the first column, at least one sign change, yes, it is a sign change. Now see here, this is nothing but plus 8 plus 3 minus 2 plus 1. Now sign is changing, positive to negative, sign changes. If any sign changes in the first column, if any sign change in the first column, now closed loop control system is unstable. Sir, one sign change, I ask one question. One pole is on the right hand side, system is unstable. Therefore, any sign changes, system is unstable. Now, the second point is, first identify the number of sign changes. The number of sign changes, the number of sign changes will give the number of sign changes will give the number of, now see here, now this is positive to negative, this is one sign change, negative to positive, this is another sign change. So the number of sign changes will give the number of closed loop poles, lies on right hand side of S plane. Now let us take in this example, there are two sign changes. If there are two sign changes, which one sign change, system is unstable, sign change, system is unstable, two sign changes, therefore there are two closed loop poles which lies on right hand side of S plane. If the closed loop poles is on the right hand side, system is unstable, okay. Now this is the condition 1 failed. Now ask one more question, sir, condition 2 is failed. Condition 2 means first column quotient should not be 0, but if any quotient in the first column is 0, what happens, sir? We will see. While solving the problems, we have that particular situation. There we will see how to rectify that one and what is the problem we are facing. That also we'll see. Okay, first you take this one. Okay. Now we will see a second situation is failed. What happened? Okay, while solving the problems, we can go through that situation also. Now we'll take a characteristic equation s square plus 10s square plus 25 is equal to 0. Now this is the characteristic equation of order 2. Am I not? This is the characteristic equation of order 2. Now for this particular characteristic equation, what about the closed loop control system stability? Without a second thought, we can easily find. Now what is the roots? S plus 5 whole square is equal to 0. A square plus B square plus 2AB, 2 into 5, 10. Okay. Now where are the roots? The roots are minus 5 comma minus 5. The poles are available, visible, and which are repeated poles on the left hand side. System is stable. Now without the second thought, the system is stable. Okay. Sir, this is the characteristic equation of order 2, but now I am unable to find the roots. Then can we identify the system is stable or not? Yes. The same problem we will solve with this s square plus 10s plus 25 equal to 0. This is nothing but as square plus bs plus c equal to 0. Now this is the characteristic equation of order 2. Now I can compare with this. If A is greater than 0, if B is greater than 0, if C is greater than 0, you just check what is A. If A means here 1 is greater than 0, correct? B means 10 is greater than 0, correct? C means 25 is greater than 0. This is correct. If A is greater than 0, B is greater than 0, C is greater than 0. Now if all are greater than 0, closed loop control system is stable. If A is greater than 0, B is greater than 0, C is greater than 0, if all are greater than 0, closed loop control system is stable. This is for order 2. Okay, this is for order 2. Yes, is already greater than 0 stable. And if find the roots, will we use the same answer or not? Okay, note down this. Clear now? This shortcut method you should be follow for order 2. Now s square plus 100 equal to 0. This is also order 2, very easy. For order 2 there is no need of doing anything. Okay, we have available the roots. S square equal to minus 100, s equal to plus or minus j10. Now what are the poles? One pole is at plus j10, another pole is at minus j10. When the poles is on imaginary axis which is not repeated, then the system is marginally stable. This is the marginally stable. Now this is also I can use with the shortcut method, the same method which is here. Now which is nothing but this is the question, s square plus 100 equal to 0. Now if this is the characteristic equation, if order 3 sorry, order 2. If A is greater than 0, yes, is correct. What is A? 1 is greater than 0, matching. If C is greater than 0, yes, what is C? C is 100, greater than 0. If B is equal to 0, there is no S term. Yes, therefore, here B equal to 0. If this is correct, A is greater than 0, C is greater than 0. If B equal to 0, then the closed loop control system is marginally stable for order 2. Clear or not? The closed loop control system is marginally stable for order 2. Now this is the characteristic equation of order 2, and this is also a characteristic equation of order 2. Therefore, when the second order system, sometimes we need this type of conditions which is useful for directly solve the problems. Okay, you do that one wherever you require, and roots are available, then there is no need of all these things. But sometimes it is also useful to you. This is for order 2 problems. Okay, note on this. Now we'll use up from the third order such that you have the RH tabular form and you have all the analysis or comes into the picture. Now we'll take one question. Now this is the characteristic equations: SQ plus 8S square plus 4S plus 1 equal to 0. This is the characteristic equation of order 3. Now let us check with SQ is an odd power. Write all the odd power quotients: 1, 4, 0. Now SS square even power, write all the even power quotients: 3, 1, 0. Now this is the two rows. Now third row you have to calculate it. The third row onwards we have to calculate the quotients. Now S power 1, 3 into 4, 12 minus 1, 11 by 3. 3 into 0, 0. 1 into 0, 0, 0. Now S power 0, x into 1, x minus 0 by x, which is 1. And I am already saying the last row first element must be a constant in the characteristic equation. Yes, it is matching. Okay. Now what is the first column? And this is the first column. This is the first column. Positive, 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 positive. All are same sign. Condition 1 is fail. Same sign. Same sign. Condition. First condition is true. Second condition. The first column quotient should not be 0. Not equal 0, not equal 0, not equal 0. First column quotient should not 0. First column quotient should not be 0. Now the second condition is also true. The same sign, first column quotient should not be 0. Therefore, if these two conditions are satisfied, system is stable. Closed loop control system is stable. If the closed loop control system is stable, and another third point, what is order 3? Well, sorry, what is order? Order is here 3. So this is the third order system. System is stable. Therefore, all the three closed loop poles lies on left hand side of S plane. All the three closed loop poles lies on left hand side of S plane. This is the closed loop control system stability. Am I not? This is for RH criteria, sir, and it will take some time, sir. Now without doing this, then can I have any shortcut method? Yes, there is a shortcut method for that. That's what I'm giving this. Now this is s cube plus 3s square plus 4s plus 1 equal to 0. Now this is the characteristic equation of order 3. Find the internal quotient product. This is the internal quotient 3, 4. And these are the external quotient. Take the internal quotients and take the external quotients. Take the internal quotient products. What is the internal quotient product? 3 into 4. 3 into 4, which is 12. And take the external quotient product 1 into 1, which is equal to 1. Okay. Now the internal quotient product is 12. External quotient product is 1. If the internal quotient product is greater than the external quotient product, now the internal quotient product is 12, external quotient product is 1. If the internal quotient product is greater than the external quotient product, closed loop control system is stable. Internal quotient product is greater than the external quotient product is satisfied. And lastly, constant. What is the constant? The constant is 1. Whatever may be the constant. The constant must be greater than 0. If these two conditions are satisfied, constant is nothing but here 1, which is greater than 0. If the internal quotient product is greater than the external quotient product, closed loop control system is stable. The internal quotient product is greater than the external quotient product, closed loop control system is stable. This is the shortcut method. Closed loop control system is stable. Now next question onwards, for order 3, don't do that lengthy procedure. Use this shortcut method. You can get the answer. Okay, note down.